So, good afternoon to everybody. In these few slides, I'm going to show you what's Baker Hughes' vision for what concerns the contribution that rotating equipment and gas turbine in general, in particular, can give to the CO2 footprint reduction in the near future. We are going to talk about fuel flex, how we can use gas turbine with hydrogen and other type of fuels to reduce CO2 footprint. We are going to talk about how we can help on this direction using new thermodynamic cycle with supercritical CO2 for what concerns heat recovery, waste heat recovery opportunities, as well as new cycles. I'm referring in particular to Lamar cycle. And then I will show you how the additive manufacturing technology can play a significant role in this performance enhancement of rotating equipment and as well as I was saying, CO2 footprint reduction. When I was preparing this presentation, I was impressed by a document, a NASA document talking about pulse detonation, which is another technology to increase gas turbine efficiency. If you look at the top left of this chart, you can see that gas turbines in the world consume about 10% of energy, and that 1% of efficiency increase, which by chance is not 1 point, is 1%, is like to have 70,000 plus wind tunnel installed in a shot, okay? So you can imagine how increasing efficiency of rotating equipment might have a huge impact on CO2 footprint reduction. Think about those numbers, because those numbers, the ones that are driving later on all the presentation that I'm showing. So increasing efficiency and reducing CO2 footprint can be done with increasing cycle efficiency through new gas turbines, as well as bottom cycle, and we will talk about supercritical CO2. We will see later we have receiving more and more requests of fuel flex, so gas turbine that, as a colleague of mine said, has to be agnostic and being able to burn whatever is coming in, and in particular high percentage of hydrogen through refinery plant and so on, which is a plant efficiency optimization and in turn a CO2 footprint reduction. And the last frontier is to have rotating equipment, not necessarily only gas turbine, able to manage 100% hydrogen fuel, okay? Which is something that is already here for some extent and is going to be developed pretty quickly in the next years. So, if you look at the fuel panorama, this chart on the top left represents the last years of bids, of requests coming from customers of different type of fuels. What we have observed as an oil and gas company is a significant shift from natural gas and nitrogen fuel rich gas to the other side of the story, so fuels that have C2 plus and hydrogen content fuel, okay? In the last year, just to give you a number, we have observed a kind of increasing of about 30% of requests of customers that are asking to burn hydrogen-rich fuel for many reasons, mostly for plant efficiency. Now, burning hydrogen is not so complicated. The real problem is to burn that in a clean way. So, dry Lennox system able to meet and be below 25 ppm. We are not yet there. There are a lot of challenges to be overcome, and that my colleague from DLR, I think, made a good explanation. I'm going to talk the same point for some extent in my presentation. There are technology challenges to be overcome, but we are not far from being able to manage such a kind of fuel or other type of fuel derived from hydrogen in the near future. Other fuel means ammonia. Why ammonia? Because it has the possibility to be easily stored versus hydrogen. You can store ammonia at 8 bars rather than 200, 300 bars. You can burn in a gas turbine, and it contains much more hydrogen per cubic meter of ammonia than 1 cubic meter at 100 bars of pure hydrogen. The two fuels have several critical points. For what concerns the engine operability, they are both a little bit complicated for what concerns engine startup. We are already able to light off the engine with pure hydrogen, but it's something that needs to be done carefully because of explosion possibilities. As well as ammonia, you have a low reactive fuel that is not easy to be started up. Flame detection, which is another security device in a gas turbine, it's a little bit more complicated with hydrogen. If you look at on the bottom left part of the chart, you can see the difference of our combustion system running with pure natural gas in a premix mode, the one on the left, and you see a light blue flame that can be easily detected, while on the right side you can see 100% premixed, low emissions, just a lab, unfortunately not an engine, running with 100% hydrogen, and it's clearly evident that we have some problems on detecting the flames. The shape is completely different. To manage such a kind of fuel, we might need to modify part of the gas turbine. For example, the combustion system needs to be different. You might have a higher pressure drop, which means lower gas turbine efficiency. All those stuff has to be taken into account while you are designing the gas turbine for this new fuel. Last but not least, having to deal with synthetic fuel, meaning hydrogen and ammonia, you can also build a mix and create the fuel for a given burner rather than designing the burner or the combustion system for a given fuel. So that's the kind of flexibility we are thinking about, we are working on to develop next generation of gas turbine able to be coupled with the renewable energies and be able to be complementary in the CO2 footprint reduction path. The methodology used so far to design gas turbine and combustion system in particular was the one that I'm showing here. So, quite expensive combustion test and massive utilization of computational fluid dynamics. The computational capability are so enhanced so far that we are able, for what concerns standard fuel, to be able to design the combustor on paper and just run for final validation. This is not, unfortunately, the case for the new fuels I was mentioning before, which means that the effort, both economical and in time, to develop such a kind of system is going to be longer than what we can expect, because we need to go back, let me say, to the original path, where you have to do a lot of component tests, tune your model to the reality of what you have measured, and later on try to extrapolate. So just to give you a flavor of the difficulties that are there, but again, the technology path is well defined. If you look at where we are now, for example, on the medium to small gas turbine that we have in our portfolio, we are already, of course, able to burn and start up with 100% hydrogen using steam or water injection for NOx control. The next step, following the path I was showing you before, is going to be to use the same combustion system, similar combustion system, to get the 100% hydrogen or the combination of fuel that we want running in a clean mode, which means hopefully single-digit emissions, but at least 25. Again, we are not yet there, but we think that will be something that is achievable in the next 3 to 5 years. Okay? Now, going back to the chart I was showing before, that 1% efficiency increase, the famous 33% more wind turbine installed. Let's see what we can do with the supercritical CO2. This is a working fluid we have been studying since a lot of time. There are several other companies that are working on that because it appears very attractive for many reasons. First of all, it has a small size plant because you are running 300 bars rather than 70. You are running with high molecular weight fluid, which makes your rotating equipment much more smaller than what you have on a typical Rankine cycle using steam. Order of magnitude is 10. Doesn't mean that you have a factor of 10 reduction in weight because having to deal with high temperature and high pressure, thickness of the wall of the heat exchanger, pipes, and so on are not negligible. The working fluid is pretty stable, and it is possible to use dry cooling, which is it is suitable for different environment application. There are some challenges. By the way, there are typically two types of supercritical CO2 application. The low temperature, which is the blue one or purple one in this chart, which is mostly on waste heat recovery, and the high temperature is mostly used or studied for the concentrated solar power application, as well as oxy-fuel combustion. So where you add fuel to a thermodynamic cycle. The challenges that we have is on combustion system itself. Working at that pressure and that temperature is not easy. We have corrosivity problems, and we have, of course, as I was mentioning before, high pressure and temperature, which is making this exercise not easy. There are in the world a few pilot cases that are working on, and on which Baker Hughes is supplying parts, mostly rotating equipment, turbine and compressors. Typically, turbine are axial turbine, while compressor are centrifugal compressor due to the high pressure that we have to realize. As you can see here, there are indirected heated, which are very high efficiency, and the directed, the Hallam cycle, which are even higher. But of course, the Hallam cycle need to go together the CO2 capture and sequestration, because you burn fuel to heat the temperature from 500 degrees C up to 1,000, 1,200. But clearly, you need to take out the CO2 you are producing. Otherwise, it's not a green application. We have done some study also with big oil and gas company. The one that you see on the left are real case studies, something that is we will be able to do it right now. And it's always a kind of compromise between cost and efficiency. If you compare the two, one is very simple, the other is a little bit more complicated. You've got two different impact on efficiency, 22 versus 27, but 22 on a 40% gas turbine efficiency in a combined cycle means you are close to 48. If you are at 27 for the same gas turbine cycle, you are above 50%, which is not 60% of a combined cycle plant, but it's clearly a significant power and efficiency increase of the gas turbine cycle itself. Okay. Now, how these two macro trends, fuel flexibility and hydrogen, as well as CO2, supercritical CO2, are connected with additive manufacturing. Additive manufacturing is known for several reasons. First of all, the new product development time, so you can print out your parts without spending money in investment casting and so on. but I want to drive your attention to 2 points of this chart, which is performance improvement as well as flexibility. There are several technologies that are used. You can see on the central part of this chart. We use some of them for building already impellers. Rather, other are used for building burners, the powered bed, and other for building some, let's say, raw material for liners and sleeves and so on. And these are already real cases. So the current production is already taking into account additive manufacturing advantages on our gas turbine. Just to think about hydrogen, if you have to run hydrogen, you might have some problem with sealing. So the solution here is to have a burner, you can see on the left part of this chart, which is not anymore made by different pieces, but it's a single piece. So you're not going to have any kind of problem on sealing. More and more, we can easily and on-the-job basis change shape, size, and so on to accommodate different fuel composition. So this is an example on how additive can play a role in the CO2 footprint reduction. Other activities that we are doing is on first stage nozzles. First stage nozzles. We are already able to build gas turbine first stage nozzle with additive manufacturing, which means that we can change the thermodynamic cycle of the gas turbine to match what are the requirements of the bottom cycle. Very easily. If you change the pressure ratio, you increase it a little bit, you are going to get lower exhaust temperature on the gas turbine and vice versa. So you can easily adjust the engine configuration without being forced to do investment casting, expensive investment casting in time, just changing a 3D model on a piece of paper. And this is something that we are already doing on specific case. Okay? So, as simple, we believe that in this transition period, gas turbine might have a significant role to play, especially, and this is our vision, in a medium to small size, so distributed energy. Possibility to install gas turbine where the energy is, talking about wind farm, for example. The fuel flexibility is the key, so we will need to have gas turbine able to run with different fuels and the same hardware, otherwise there will be no game. CO2, supercritical CO2, especially if we can modularize for some extent the elements and the big block can play a significant role in efficiency increase of the existing plant, because, as I was saying, very small footprint. And as I was saying, additive is going to be a kind of salt and pepper mixed and used to be able to enable the technology that we have to develop in the near future. That's all on my side. Thanks for the attention. Sorry?
Okay. Thank you, Alessio, for this very interesting presentation on the research and development within Baker Hughes. I had one question. You mentioned about ammonia and the opportunity to maybe to burn in the future, to burn ammonia directly, not to have any losses, converting it to hydrogen again. Where are you on a technology readiness level, burning ammonia directly in the gas turbine? Because that is, of course, a major challenge.
We have done really only some component tests demonstrating that it's something that can be done. As I was mentioning in my chart before, it's going to be a kind of building the right fuel for a given combustion system. So, to make an example, the burnability of ammonia itself it's relatively low, while hydrogen is high. So we may end up of mixing the two at a certain percentage to find the right fuel composition to get the stable flame, low emissions, and flexible. But while for hydrogen we are already at a certain level. As I was mentioning before, we have already done fully premixed component test successfully. Then move from fully component test to engine is going to be a long journey. It's not right behind the corner. On ammonia, it's a journey that is starting up right now, or at least on our side. But we believe that is a kind of working fluid, combustion fluid that need to be evaluated and to understand which are the potential benefit on that.
Okay, thank you very much. Any urgent question? Okay, then we move on to our next speaker. So thank you again, Alessio.